I think it's better if we wait a little bit. Okay, now I give you a suggestion, and given that we will see each other in a long time from now, I think it is a good idea if I give to you an exercise beside this one. My suggestion for you, it's a kind of homework. You don't need to present it to me. It's a suggested homework. My suggested homework is try to redo this program without looking at the suggested R file. Just try to remake it. And once that you succeeded, of course, if you have problems because you don't understand something, the easiest way to learn what to do is to look at the suggested R file. But try to minimize the times that you look at it in order to get independent. Once that you did it, if you succeed, my suggestion is to give you an additional exercise to write a code for computing, for applying the linear reservoir rainfall runoff model. And then the next exercise that we will make together is the application of IMOD. So my plan is when we meet again, which will be on April 16, we have 2 hours, I introduce the theory, I complete the theory of IMOD. And then the next day, you bring your PC, which is April 17, and we apply IMOD. Together we write the code, because it's a bit more complicated with respect to the linear reservoir. Now let's instead give to you as an homework, optional of course, an exercise on the application of the linear reservoir. So let me first of all show it in my website. I need to show it, just 1 second. Give me 1 minute. Okay, now it's visible. Now, if you look at the web page, you see that there is one more link, exercise, application of the linear reservoir rainfall runoff model, and there are 3 lines. There is rainfall and evapotranspiration and river flow data. Because in order to apply a model, of course you need rainfall and let's forget about evapotranspiration for now, because it's something that we didn't discuss. Let's focus just on the first column of this file. This is the file. If you click on it, you see that there is written, the first column is hourly rainfall, the second is hourly evapotranspiration. And you may forget about evapotranspiration, second column. And also there is a column of river flow data. The river flow data allows you to compare the output from the model to the corresponding river flows. It's not needed, the river flow data, for running the model. It's needed for comparison. Okay, and let's look at the exercise. It's a PDF. Basically, it says, sorry for the subject, advanced hydrology, I need to change it. Application of the linear reservoir rainfall runoff model in a catchment whose area is 1214 square kilometers. Rainfall data have been observed at hourly time scale for a period of 1 year. The related observations of mean hourly rainfall in millimeters per second can be downloaded at my website. And also there is the hourly river flow, and it says, by assuming that the runoff coefficient is equal to 0.5, which means that you have to multiply each of the rainfall data by 0.5. You remember the rational formula, the runoff coefficient is just a multiplier of rainfall. It is required to model the rainfall runoff transformation for the catchment by applying the linear reservoir method. Okay? And it says, note that evapotranspiration data are included in the above file, which are not necessary to apply the linear reservoir if a runoff coefficient of 0.5 is assumed, because by introducing the coefficient of 0.5 you are already accounting for losses, including evapotranspiration. And then there is written explaining a brief report about elaboration. Forget about it. I will change the text by removing the last line and changing the name of the subject. I will do it today or tomorrow. Meanwhile, you can download it, because this is what matters. And it's not easy, I tell you, because you need to apply a numerical solution. What you need to do is, in R, it's very simple, but let's clarify it. Linear reservoir, it's a bucket model, as you remember, which means that you have rainfall, which you know, going into it, for hourly rainfall for 1 year, and you have river flow out of the bottom discharge, which is equal to, remember, storage divided by a constant. So first of all, you need to fix a value for the constant. And a value for the constant could be something like, by guess, you need to guess it. But I give you an order of magnitude. The order of magnitude could be something like, just 1 second, 50,000. And then what you need to do is, at each time step, so you need a cycle here, what you do is, basically, computing WT. Let me say WT plus 1, which is equal to WT plus P T plus 1. So you take the previous storage and you add rainfall. And then you compute Q T plus 1, which is equal to W T plus 1 divided by K. Perfect. Be careful. At this stage, you need to update the storage T plus 1 by subtracting W T plus 1 is equal to W T plus 1 minus, I put a plus here because minus would be plus, minus plus is minus, okay, minus K Q T plus 1 So you understand what I did? I started from the previous storage, I added rainfall, I computed the outflow, and then I am updating the storage by subtracting the outflow, because at the same time you have something entering into the reservoir and something going out. Be careful that there is an approximation here, because you may ask me, why do you first add rainfall and subtract the river flow? Why don't you do the opposite? I could first subtract the river flow and then add rainfall, I would obtain a different result. The different result, what is the difference? The difference is due to numerical approximation, because in doing this, I am applying a finite difference method. I am moving forward for delta t time steps, not dt. This is not an analytical integral. What I'm computing here, look, it's just a summation. A summation is an integral. So I am indeed computing an integral here, but it's a numerical integral. So I'm not applying the analytical integration in order to get the solution of the linear reservoir. I am applying the numerical integration. The reason why I'm doing that is that rainfall is not constant. If rainfall was constant, I could indeed apply analytical integration. It would be much easier and more precise. Rainfall is not constant, so I cannot use analytical integration. Look at the linear reservoir and you understand that. Okay, of course, in doing this, there are approximations. Numerical integration, numerical analysis, involve approximation, and I'm sure that you had some courses focusing on stability of numerical solutions. I don't want to recall back these details. I just want to tell you that you need to make sure that due to numerical approximation, you don't get meaningless results. What could be an example? Here, you could get a negative storage if you don't pay attention. So you need to put a condition in order to avoid this. And the condition in R would be, let me write it here. If square parenthesis WT, keep in mind that in R you cannot write WT. You have to just use a variable W that is updated at each time step. So you wouldn't write here WT, but just W. Minor less than 0, you go to the next line, WT is equal to 0. This is a condition to avoid negative values. And then that's it. You can run your program. Of course, here I didn't put the runoff coefficient of 0.5. You need to multiply rainfall times 0.5. And you can see what happens if you play with the k value. The k value is defined at the beginning in your program, in your code, like k equal to 50,000. You can reduce k to 20,000 and see what happens. It's very interesting. And then, if you want, you can make some considerations. What is k? What happens if I put a k that is smaller? What happens if I put a k that is larger? Remember, anytime that you make a code, it's very easy, even if you are an experienced programmer, it's very likely that you make mistakes. Because it's an activity that is subjected to a lot of possible mistakes, programming. So what I suggest to you is, before running the model with the real data, try to run the model with something for which you know already the result, like constant rainfall. Try to guess what is the result that you expect for constant rainfall. And try to run the model with constant rainfall and see if you get that result. And then, if you see that you are happy, then you run the program with the real data. One more thing, be careful of the units. You have the catchment area in square kilometers, rainfall in millimeters per second, and you want to get the river flow in cubic meters per second. So think about the units. It seems obvious, but this is the most likely mistake that you make. Because remember that PT is not rainfall depth, it's rainfall volume. So PT in the linear reservoir is rainfall depth times the catchment area. I'm not expecting that you succeed with the exercise at the first attempt. And as I said, it's an option. If you don't succeed, don't worry. We will start with IMOD, which is more difficult. Once that you learn to apply IMOD, then you can easily correct the linear reservoir where you eventually or possibly made a mistake. But I think that if you spend just not a long time, I suggest that you spend no more than 2 hours on that. Three hours. I'm sure that you can succeed. Okay, this is my suggestion, but don't worry, it's an option. And if you just are fine with the flow duration curve exercise, then we move forward with the next one, and you don't lose anything. It's just an opportunity to get a bit more skilled autonomously. Perfect.